Hi, everybody. Welcome back to Everyday Metallurgy, the podcast on metallurgy in your everyday life. Today, we're going to look into the powder manufacturing of metal powders. And I have invited a grand old man in this field, Paul Davies. He has been making powders for, yeah, more years than I've been working with metallurgy. So please welcome Paul and learn from one of the experts. Hi, Paul.
Good day to you, Peter.
Welcome to the podcast on everyday metallurgy.
Thank you for inviting me.
Paul, you have been waiting for a long time to talk on this channel because you are from my old family in powder production, because that was also where I started my career. We have crossed our lines previously. I have been working on the spray forming process from Osprey, and you have been an Osprey guy for many years. But could you start introducing yourself, who you are, your background, and where you are today?
Yeah, certainly. My name is Paul Davies, and I'm based in South Wales, which of course has a very rich industrial heritage, dating back hundreds, if not thousands of years. Educated locally, I did physics and material science, which is a very good background to bring into powder metallurgy. So absolutely. So I actually joined Osprey Metals, as it were called, back in 2001. And worked for them for several years in a technical sales role. And then I also worked for Tata Steel, which of course is a different scale of manufacturing, strip products based again in South Wales, but also visited many different facilities throughout the world, actually. And then rejoined Sandvik, who are, of course, manufacturing metal powders in South Wales for 10 years. And then more recently joined IndoMim, who are, of course, one of the largest metal injection molding companies in the world, and now have interest in powder production as well.
Yeah, and that's the theme today. That is powder production, because powder is used in so many places. And what people most recently think of is powder for additive manufacturing, the 3D printing. But you also use powders for hip products. You use powder for metal injection molding. You use powder for standard Press&Sinter. You use powder for spraying. So there are a lot of applications to use powder. But today, I think we will mainly look into the gas atomized powders. Am I right?
That's right. Yeah. So I've got a basic introduction to IndoMim first of
Yes.
all, and then a brief overview of different metal powder production processes, actually, and they of course are many different forms. Then, as you said, I will focus on gas atomizing, both vacuum, electrode inert gas atomizing, and then try to find what the more recent technical developments are. Finish off with talking about sustainability, and I'll summarize at the end.
Yeah, perfect. So where should we start? Should we look into how do you make powders at all? How does a factory look like? Do you have some
Yes, I can share some slides with you for sure.
important?
Let me put them on the screen. There we go. Oh.
Yeah, because it is a standard process where you melt the steel or the metal, and then you put it through a nozzle, and you atomize it. And I used to compare it with when I was a kid. I was playing with my sisters in the garden with the hose with water, and trying to spray them. So when it came out of the nozzle, it was just like a tube. But when I adjusted it, it spread out.
Exactly, yeah. And that is a key part of the technology indeed. And I hope you can see the screen now.
It worked fine.
Okay, terrific. So yeah, as I said, I'll do an introduction to IndoMim very briefly, highlighting their diverse technologies, in fact, both metal injection molding, ceramic injection molding, more recently investment casting, precision machining, additive manufacturing, and now, of course, powder production, based predominantly around gas atomization. So yeah, IndoMim, they're a growing company. They have several hundred components manufactured every month. More than 250 molding machines, and they're making their own mold tooling as well, which is quite an important subject. And yes, have a wide range of different material options for metal injection molding. So low alloy steels, tool steels, stainless steels, nickel, cobalt, even titanium, as well as then ceramic materials as well. A global footprint, of course, located and headquartered in India, but also have manufacturing facilities in the UK and the USA, and more than 4,000 employees these days. And yeah, shipping millions of metal injection components around the world. So here you can see our global footprint with production UK, North America, and headquartered in India, with sales offices around the world, including in Asia as well. And here you can see some of the components produced by metal injection molding. Small, complex components, leveraging the molding capabilities and the raw materials, which of course is composed of a combination of polymers and fine metal powders that are sintered.
And well, how would you say the difference is between MIM and additive manufacturing today? So how you can make more complex shape with additive, but are we adding 10% upon the MIM, or is it 50%? How close are they together?
There's a good synergy between additive manufacturing and metal injection molding. Of course, with the molding, you do need to make a mold, and that's important. So therefore, the cost of making that mold has to be taken into account in terms of the number of components. So additive manufacturing, which can produce components with, as you mentioned, a slightly higher degree of complexity, because you can have, of course, internal structures. Whereas metal injection molding, you are limited in terms of the three-dimensional capabilities and overhangs, but not internal structures per se. But you can leverage both laser powder bed fusion and binder jet printing, which of course is itself a sinter-based additive technology. And we actually use that technology to manufacture inserts for mold tooling. And here you can see what is a conformal cooled a mold injection component. So this is just a slice through, and you can see the conformal cooling channels. So we're printing these using binder jet printing for our own metal injection molding requirements. So in this case, we use M2 tool steel, because it can reach 65 HRC, and which is a high hardness, very good wear resistance. And that's important when you have a fine abrasive feedstock like metal injection molded feedstock. So as I said, we're making our own metal powders, vacuum inert gas atomized, both for additive manufacture, thermal spray, and we utilize these equipment for our own MIM powders internally as well. But of course, we do buy powders on the market as well. And the grades manufactured are stainless steel, cobalt, nickel, tool steels, low steels, and cobalt chrome, and a growing range of different alloys, in fact. Making them using high quality capabilities, and that's important to have the appropriate levels of standards as well. So both aerospace, automotive, medical, environment, quality assurance, of course, clean room, health and safety, and energy efficiency as well. So this covers not just the MIM process, but a range of different technologies that we employ, including casting and machining as well. So what I do have is a short video, just a couple of minutes.
That's what I've been looking forward to all the time.
So I had the privilege of going through the IndoMim powder plant back in September. So I did a quality and health and safety audit while I was there, because I've visited a number of different powder plants over the years, so I could put that in perspective. And so why don't I show you the video I have ready to go?
That'd be great.
So this is a video which is on YouTube already. So hopefully you can see the screen. And I've cut the sound, so I'll talk through it myself and just give you a highlight.
Yeah, that'll be great.
So here you can see the storage facility, a nice color-coded drums, which is a nice touch, and the gas atomization facility. So this is a vacuum inert gas atomizing plant. Actually, they have two of these in place, as well as an air melting system as well. So there you can see putting the top on top of the chamber to make the hermetic seal for the atomizing chamber.
Yeah. What is the tonnage of the Vega system?
Each one is around 250 kilos.
Okay.
So they have plenty of capacity because they can run basically 24 hours. So melting appropriate raw materials. And when it comes to safety, melting under vacuum is basically more safe than melting under air, because air can react to the alloys, create carbon dioxide. So that can result in a gas emission from the molten material. So therefore, excluding the gas is important. A full range of sizing capabilities as well, sieves and air classifiers, and of course the quality assurance is very important. The flowability of powders is often very critical for additive manufacturing, so that's tested in a full metallurgical lab, as you can see here, and various equipment including laser diffraction equipment and sieve tests, and looking at morphology. And yes, laser powder bed fusion, e-beam powders, DED, and binder jetting, which we use ourselves internally, thermal spray, and powders for MIM. So that's what the facility looks like. It is a world-class facility. It's safe. The lost time injury frequency rate is currently 0 and has been since I've been working for IndoMim. So there we go. I'll continue the slides now. Okay.
Yeah. Perfect. If we dig a little deeper into the powder manufacturing and we talk about gas atomization, then you could atomize with different gases.
Absolutely, that's right, and I'll focus very much on gas atomization. But first of all, I think we should probably learn about some of the other large-scale powder production processes. So I've got a few slides just to provide a little introduction to direct reduction of iron powder, for instance, electrolytic, some thermochemical processes, and yes, focus then on gas atomizing. So let me restart the slides, and I can take you through them. And if you have any questions, let me know, and I can answer them as we go.
Yeah, sure, I will. The direct reduction iron, going from the ore to powder, has become a real important new technology, because it has been going on for many years. But in iron production, it is seen as the zero carbon emission technology if you can reduce it with hydrogen.
Yes, absolutely. That's one of the potential benefits going forward and from a sustainability point of view. And yes, as we can see from the pictures, the powders, they do come in many shapes and sizes as well. So we'll learn about some of these powders as we go. And of course, the morphology, the size distribution, they're all dependent on how these are manufactured, in fact. So what I've got here next is a table of different production processes and the different size distributions that they need. So for instance, metal injection molding, needs a fine powder, a high surface area for good sintering activity. Then cold spray, a kind of fine powder as well, or about 15 to 30 microns. So has to be fine to be able to be blown by high velocity gases, originally helium, sometimes nitrogen, and more recently in air, to deposit on surfaces and splat and get good metal adhesion. And then we get into the additive manufacturing processes.
This cold spray.
Yeah.
I often think the name is misleading because it's not really cold gas, is it?
It's not particularly cold. It can be 600-700 degrees C, in fact, yes. And that allows the gas to impart a lot of kinetic energy into to the metal powder. So sometimes it's called kinetic spray as well, I suppose. And that high velocity again has a good synergy with gas atomizing, in fact, because they use a converging, diverging, or de-Laval nozzle to make sure it's a very efficient process, and typically limited to relatively soft ductile metals, copper being the most famous, and therefore allowing it to splat onto the surface and form a metallurgical bond. But I guess you could call it cold because it never actually melts the powder.
Exactly.
It's more of a splatting, rather than a melting process. So it's got some advantages from that point of view.
But sometimes it's a bit misleading. I had a discussion with some guys last week about it, and they thought that cold was cold.
Well, that's right. No, but it's definitely pretty hot, and that actually we'll come back to that in gas atomizing as well, because temperature can have an influence on the efficiency of the process and the size of the distribution produced. Actually. And then laser powder bed fusion, which of course is the most popular additive manufacturing process. Sizes range 15 to 50 microns, for instance. And then you get into the electron beam, which is a little coarser, 50 microns to about 150 microns. Thermal spray can cover quite a wide range of different size distributions, actually, depending on the equipment you're using, whether it's high velocity oxy fuel or thermal spray, plasma spray, for instance. So that, depending on the technology there, that can vary. And then you get Press&Sinter, which is a kind of mid-size, 150 to 150 microns, and hot isostatic pressing pretty much uses the entire distribution.
Takes everything.
Yes, exactly. So you want those size to be a normal distribution, so the small particles fit between the large ones to get a high level of tap density and apparent density as well. So first looking at powders for Press&Sinter. Of course, this is often a reduced iron ore powder or magnetite, and the powder tends to be compressible, so it needs an irregular shape and have good green strength prior to sintering. And it's manufactured by basically a thermochemical process to reduce the powder, often in a rotary kiln or rotary hearth. And then you can use coal as the reducing agent, or as a batch or fluid bed process where you can use gases, all followed by crushing, grinding, screening, and annealing. And that's where you can use hydrogen, for instance. So you can manufacture hydrogen either from natural gases or ideally from more renewable sources using electricity, derived then from water. Use that hydrogen to reduce the iron powder. So yes, it eventually, when the hydrogen economy grows, then this process of using hydrogen to reduce iron powder will grow also. It is manufactured in massive volumes, actually. I was quite surprised. More than 130 million tons of reduced iron powder, with actually India being the largest producer.
I think, and Iran as well is large in this And then we have Höganäs in Sweden.
Yes, of course, absolutely, and also very famous for water atomized powder, which we'll come to. So there are a range of different processes for Press&Sinter. There's sponge powder, electrolytic, and water atomized powders as well. But now I mention a process called Carbonyl ion process. And the Carbonyl process was actually invented here in South Wales to refine nickel powders back in the 20s. It's also called the Mond process. And then in Germany, it was then refined to make iron powder. And it's basically a thermal decomposition of iron pentacarbonyl. So you actually react iron materials with carbon monoxide at high pressure and high temperature, and then it's a process of distilling, evaporating, decomposing. So quite a complicated process prior to then to getting kind of almost growing powder particles around a shell. So this is what they look like when you section them. But they're nice and beautiful and fine powders, which is very important.
It's like looking at a tree.
Exactly, yeah. So, and that's the kind of the carbon iron almost evolving and growing in a way. And then the same goes for nickel as well. The powders tend to be very pure, 97 up to 99% iron, with this trace of carbon remaining. And it has many applications, of course, from your iron additives to food products, so your Kellogg's and other cereals available. We have a look at the iron. This is typically where it comes from, carbonyl iron, sometimes direct reduced iron as well. But because it's very fine, it was one of the first raw materials used in the metal injection molding process as well. And then moving on to other processes like electrolytic copper. And here you can see the electrolytic baths with the copper plates, anodes and cathodes all in place, and just highlighting the scale of the copper production there. So there's around about 70,000 tons of copper produced annually in the world. So it's a huge process, quite labor intensive as well. So you have to kind of remove all the fine electrolytic copper from the plates, and this is what it looks like. It's basically a dendritic powder, so it kind of grows like a crystal. And then there's some relatively new thermochemically produced powders. So here I've highlighted the titanium or ilmenite, and there's if you apply different elements like calcium and magnesium, you can use these elements to reduce the titanium dioxide, which effectively is the ore, and then apply certain processes, including spheroidization, to make both irregular as well as spherical powders as well. And this has a lot of potential. There's some competing interests in North America as well as in Ukraine, developing this process to make titanium powders
to make it pure titanium with this process. So it's
absolutely pure titanium powder.
The Kroll process just made in powders.
Exactly, that's right. So sponge is the Kroll process, and this is a kind of refinement of that process where they're introducing magnesium as well. But they can also make alloys like titanium 6, aluminium 4, vanadium as well, by introducing the appropriate amounts of vanadium and aluminium oxides as well. So this will continue to grow, no doubt. And then, of course, we get to water atomization, where it uses high pressure water to make up molten metal streams. So this again is a high volume production processes, and the annual production is around about 700,000 tons. So it's a huge industry, and some of the big players are making 200 tons each. So it explains why there's not only so many powder producers out there making water atomized, but of course the parts, using parts for automotive industry, internal combustion engines in particular, and that market in North America alone is worth $7 billion. So it's a huge industry. It's used to make iron, steel, soft magnetic and stainless steels as well as some copper powders as well.
And as I understand it, there are two levels of water atomization. There's what we call normal pressure and then the high pressure. And I think normal pressure is around 100 bars. And the high pressure is 1,000 bars atomization pressure. Is that right?
Absolutely. I believe so, yes. And the higher the pressure, the finer the powder, and typically the more spherical the powder becomes as well.
Yeah.
Then. So it is used in high volumes in metal injection molding, especially in China, for instance, and Japan.
Yeah.
So it's competing in some regards with gas atomized powders, especially in the fine end of things. And here you can see just a little schematic of a water atomization unit with the high pressure jets, and then the evolution then of the impacting water on the molten material to create solid droplets. The lower pressure atomization tends to cool the powder quite quickly. So then you often get an irregular powder. And of course, because it's water using, then there's a degree of oxide on the surface as well.
Yeah.
So here I've got a little schematic highlighting some irregular water atomized powder with lower packing density, a thicker oxide layer compared to gas atomized, where the contact areas are higher. The oxide layers are much lower by a factor of 4 typically, so 1,000 ppm versus 4,000 ppm. So that explains why gas atomized powders are used in certain applications and for certain sensitive alloys as well. Yeah, so that's the kind of high volume atomization processes. And then at the other end of the scale, actually, we have ultrasonic atomization, which is often making really small quantities, but are alloys of extremely high value and different types of materials as well.
Yeah, so typical very reactive metals, isn't it?
Exactly. So titanium alloys and almost every element under the sun, actually, and they can be sourced from different material forms as well. So you can melt typically powder or wire, or sometimes clad wire as well, and then they can be melted by different processes like arc, plasma, or induction heating as well. So it's quite a versatile technology of melting and creating unique alloys, atomizing, and then to freeze that composition, and also make glassy alloys as well. So the cooling rate is very quick. So it's all really related to the ultrasonic aspect is a sonotron, in fact, and these create capillary waves, and you can see the little capillary waves on the screen here, and here you can see the standing waves, and then as the frequency and the energy of the ultrasonic vibration increases, they literally blow off little droplets in effect, and then they can be blown away and captured to create really beautiful spherical particles, as you see in the picture here. But of course, it is a relatively modest production volume. So you're talking maybe a kilo an hour. So it's quite modest. I'm sure it'll scale, but it's really for research applications, I suspect.
I remember when I was studying, we also looked at some alternative process called REP and PREP. So the rotating electrode process and plasma rotating electrode.
Yeah, absolutely. And in fact, we can see examples.
Do they still exist, or is it from my young days?
They do exist, yeah. So here we have plasma atomized wire. So they're basically leveraging plasma torches to melt a wire and then create metal powders, often related to titanium alloys. So if you can get in a wire source, then it's a relatively efficient process. It is limited to materials with wires, though that said. And a similar process can be used to spherodize irregular powders as well. So if you drop irregular powders or even scrap materials through plasma gases, then they can melt the surface to a nice spherical powder, as you see here. And yeah, absolutely, the rotating electrode
it is
atomizing
there.
process. It is there, yes, and often used to make coarser powders, I would say. But again, really beautiful spherical powders. It is, of course, a batch process, more or less, because you're consuming the electrode as you're going. And yeah, I remember seeing a plant making cobalt chrome alloys, and they were creating cobalt chrome powder, and they were quite coarse, 100, even 200 micron, and they were typically used to make sintered metal beads that were then sintered to a medical implant.
Okay.
And that provided a texture onto the implant where the bone could grow and almost key onto the surface of the implant. You could argue now that that's been superseded by 3D printing complex textures and surfaces on lattice onto the implants directly. So not necessarily needing so much prep powder. But again, if you can get a bar, you can make coarse spherical powder in a batch process.
Yeah. Thank you very much for following part 1 on this episode on atomization or powder production. In this part number 1, we look deeper into different high-scale manufacturing methods and some very special ones. But in part 2, that will come out pretty soon, we'll look deeper into different gas atomization technologies. So stay tuned. Subscribe to the channel, Everyday Metallurgy, and see when part 2 comes out and we dig deeper into gas atomization meant for metal injection molding, additive manufacturing, and so on. Paul is really hot now, so stay tuned. See you soon.